here we go. Hello, hello. Okay, good. Good, good. Everything all is well. Nice, nice. Blah, blah, blah. Nice. Okay, good. Alright. Let me see if I could make everything right. Everything's good. Good, good. Alright, nice. Okay, here we go. Hello, everyone. Welcome, class, to my next part of this series, or at least an attempt on this series of this answering every single problem in this classical mechanics book by Taylor. Here we go. It's pretty much this one. That guy, yeah, this book. Some of you physics people there, or undergraduates, probably recognize this book, so I might as well just, do it. just for the benefit of you guys or my own that I could refer to. All right, here we go. So I would like to make some corrections from last time, though. I did make a small mistake here on section 1.1 and 1.2 over here. So let's try to give that a little whirl. Here we go. So 1.1 over here. I actually made a mistake on the dot product over here that I did not fully follow up with the entire definition of the cross product. Did I say dot product? I meant cross product. So cross product of this one, this is actually a negative. It's actually a negative. Oh wait, why is that a? Yeah, there you go. That's actually a negative over there. I believe I put it on the comment section down below on the previous video, so I'll just make that correction. There you go. Now it's a negative. Bam. It's done. Now it's correct. What I mean by negative is negative next to the J, right there. And that'll make it the right answer for 1.1 right here for the cross product. Okay, that was part D. Now for 1.2, it's the same thing, same story, that you'll encounter a plus sign right here. It's going to be a minus over there. Nice. And this is actually a plus over here, and this is a plus over there. Okay, there we go. So the J product, the J part, the Y component, should be the opposite sign of what it was previously. So now it's correct. The dot product, the cross product between B and C over here. All right, so that's good. It's perfect. You got everything. Let me see. You know what? I should have timed myself on how much I stream. I'll make myself an hour. Okay, there you go. 1 hour. Nice. All right, here we go. So now that we made these corrections, everything else should be with full confidence. The right answers. So that seems to be very good. All right. All right, good. Now let's move on. Where did we leave off of? 1.6. Let's do 1.6 right now. Here we go. 1.6. Over here, as monitor. Got it. Okay. Here we go. By evaluating their dot product, find the value of the scalar s for which the two vectors b is equal to x plus sy and c is equal to x minus sy are orthogonal. Ooh, okay. Remember that two vectors are orthogonal if and only if their dot product is 0. Got it. Explain your answers with a sketch. Okay, cool. So this is only on the 2 dimensions. That's fine. You know what? Let's make this 5. No, not 4. 5. There you go. This is only in 2 dimensions, so keep that in mind. It's okay. And let's illustrate b first. It looks like it's going 1x and then upwards of whatever s is. So let's point that out. There you go. So this is b. This is the supposed magnitude, x and y component. So make this s. This is 1. Oh, and by the way, this is y-axis. This is x-axis. Good. All right, next one. Let's make this one green real quick. C is equal to x of negative s over there, so it's going at the opposite direction. That's fine. Point that out. And then whatever this s is. Nice. Okay. Now, it looks like we need to find the orthogonality of, basically B cross product C, right? That's what we're finding. Let me check. So S for which the two vectors be in, oh, I get it now. So B cross product C, wait, no, that doesn't make sense if we have to make the cross product. What actually makes sense is that this should be 90 degrees for them to be orthogonal. So that means let's make this a very good illustration. More accurate illustration, you know, more accurate. Okay. So this is 1. Make this B over here. Make this C over here. This should be 90 degrees, okay? This should be 90 degrees. That's what it means to be orthogonal. Okay, B, C. Okay, this is S, and this is S. Negative S, actually. Negative S. It's the origin, 0. Y, and then X. Good. We got it. Alright, so this is all set and done. Now, we could actually take a look at B is actually 1s. That's good. Well, this is what it looks like that. And C, vector C, is 1 negative s. Nice. Okay, good. Now, we pretty much do the two vectors are orthogonal if and only if their dot products is 0. Okay, that's fine. So this tells us that B dot C is equal to 0. That's fine. It's okay. And from here, we could actually evaluate what S is. So it's pretty much like this. You could do it like 1s. I'm just going through the entire process. Negative s is equal to 0. And then from here, it looks like we have 1 times 1, right? 1 times 1. It's going to be 1. Plus s times s, which is basically negative s squared. That's okay. And you have 0 right here. Nice. So what is s here? S is equal to 1. Looks like s has to be plus or minus 1. And it makes sense. There's going to be s over there. S is on the opposite direction, on the below the origin. So s has to be plus or minus 1. So it makes sense. Nice. S has to be 1. Let's just make it 1. There you go. All right. There you go. S is 1. Explain your answer with a sketch. Well, I already did it. There you go. S has to be 1. Find the value of the scalar s for which two vectors. And that seems to be... yeah. This is it. 1.6. We got it. All right. Next one. Here we go. Copy this. Taylor 1.6 done. Now Taylor, well, actually let me pause this for a moment. I didn't really do much pauses last time, just for you to see. But I guess because I was rushing last time. But okay, this one. Let's do 1.7 now. There you go. Alright. Prove that the two definitions of the scalar product r.s as rs cosine theta 1.6 and sum of risi 1.7 are equal. Ooh. One way to do this is to choose your x-axis along the direction of r. Strictly speaking, you should first make sure that the definition 1.7 is independent of the choices of axes. Definition. Okay, let's look at the definition at 1.7 here. And 1.6. Yep, 1.6 right here. All right. Where's 1.7? Where are you at? Six, 7, got it. Okay, r.s, and you have that thing. Cool. All right. So this is what we're proving. These guys. There you go. It's from the book. Prove that the two definitions of scalar product r.s as rs cosine theta and sum of rs are equal. Okay. So choose your x-axis along the direction of r. Choose your x-axis along the direction of r. Along the direction of r. Strictly speaking, you should first make sure that the definition 1.7 is independent of choices of axes. Ah, okay. 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 How would this work? Should first make sure that the definition 1.7 is independent of the choice of axes. Niceties problem 1.16. Oh. Okay. Well, we're not there yet. You know what? Let's go from left to right first. Here we go. Let's do this. RS. Actually, let's draw the graph first. Draw the graph. So we have this thing going that way. R is going that way. That's okay. Some arbitrary vector. And then I'll do some arbitrary vector as well, going that way. That's fine. This way is fine. Okay, good. And then this would be S. Vector S. This is vector R. Nice. And this would be theta. It's okay. Well, they're gonna have their own lengths. That's good. One way to do this is to choose your x-axis along the direction of r. Choose my x-axis. So what I'm saying is that if r is like down below over here, if that's the case, let's try to do that. Let's do that real quick. So r is the x-axis. How about that? Let's see what happens there. R is the x-axis. R is along with the x-axis. That's more proper to say. And then this one is right here. Wait, what is it again? S, yeah. This is R, and is the angle. That's fine. Okay. Now that we chose this guy, let's see. The R is going to have a length, right? It's going to be R. And then multiplied by... wait, that's going to be X. Yeah, that's going to be X. XR... Wait, I'll do it like this instead. So R, magnitude, is equal to x squared plus 0 squared square rooted. It's basically x, not xr. I'll call it xr. There you go. And then S magnitude is equal to xs squared plus ys squared. That'll be better. Yeah, I'll keep it as that. Okay, after this, what now? That'll be cosine theta. And cosine theta would be this guy. Let's see what happens if we do this. So this is basically a triangle, right? That's a triangle. Nice. No doubt about that. And it looks like that cosine theta can be expressed into something else. So let's do that. Cosine theta. Magnitude of R is basically that one. And magnitude of S is that guy. So this is basically the hypotenuse. This is the adjacent. And cosine is SOHCA, adjacent over hypotenuse. Adjacent over hypotenuse. And it's going to become adjacent. Where's adjacent? I keep forgetting. What is adjacent? XR. There you go. XR over. And hypotenuse is S. S squared plus ys squared. Got it. Cool. Alright. That makes sense. What are the x-axes? Okay, it looks like I only did 2 dimensions, so let's try to add the z-axis as well. Let's do that. CS squared. That'll be good. This one is... I made it to a 0, so that means... I made y equal to 0, right? So, I'll just add a x-axis, z-axis right here. Z, y, x. So that means this thing is going to move along here. Let me morph this real quick. Whoop. And it's going to be like... Oh, that looks bad. It's going to be like... How do I skew it? It's like... Rotate. That looks pretty bad. But I guess I'll have to do that. There you go. That looks bad, but I'll take it. I just want it to be in the middle of the I just want it to be in the middle of the plane. That's all. Good. Sorry. And then this is R. Okay, good. So this tells us that R is at, so y is equal to 0 over here. And then z is 1 left over here. ZR squared. That's better. So that means this would become this guy. Can I do that? Other axes. Choices of other axes. One way to do this is to choose your x-axis along the direction of R. 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 along. I mean, yeah, it is. It is along with it. Okay, that's fine. Wait, you know what? I think it would make sense that this would be. All right, let's go back a bit. Let's go back. Let's put it back like this. Let's put it back like that. That'll be way better, because it did say to go. The r should be, your x-axis should be along with the direction of r, so it is indeed along with it, parallel with it, right? So I would just keep it that way instead. Okay, here we go. So this one has to be. Oops. So this one has to be 0 squared plus 0. Yeah, 0 plus 0, whatever. And then this would be xr. Better. And then you would have the z-axis here plus zs squared. Good. So that's your cosine. I think we solved what the cosine is. So altogether, we have rs cosine theta. We could put it together like this. I'll just say, hence, rs cosine theta is equal to this guy, xr of xs squared plus ys squared plus z s squared. Let's see if this works. Okay, that's the s version. And then this would be the cosine theta. And you have xs squared plus ys squared plus so wait, cosine is so adjacent over hypotenuse. Yeah, okay, good, got it. Plus ys squared plus z s squared. Oh, I think some things are canceling out over here. xr. Yeah, like this guy and then this guy, right? And then this would turn into xr squared for some reason. Ooh. Okay. So that's xr squared. Does that ring any bells? Let me think. So r1, s1, xr squared. This guy, pretty stumped here. Let me think. What would be a very good one? Scalar product of this guy is going to turn into that. And, oh, yep, what's up? Yeah? Okay. Where was I? So you have this guy. Xr squared is going to turn into that. That's pretty weird. The scalar product r dot r is often abbreviated as r squared. Ah. Let me try to think of this. How would you come up with this? So rs turn into that. Am I missing some stuff? Let me try to get some stuff here. Rs cosine theta, rs, and then r2. So that should be together. One way to do this is to choose your x-axis along the direction of r. So that's going to have an x only. Got it? And then strictly speaking, you should first make sure that the definition 1.7 is independent of the choices of axes. Axis. If you'd like to worry about this, okay, we don't need that. I mean, okay, what about the r dot s is going to have? Okay, r dot s. Let's analyze this one. So altogether, you're going to get x right here, right? So r, and then dot product with, I'll do it like this first. 0, 0, and dot product with s whoops, ys, Wait, no, xs, ys, and zs. There you go. Better. And putting it as a dot product, you're going to get xr xs plus, going to get a 0, and plus 0 plus, okay, that's it. Oh, wow. Okay. So that's what it looks like when you do that. And it makes sense. Look at that. This one is basically saying R1, S1. That one. I got this notation. I should have done this notation more. But okay, so that's R1, S1. How would you do the rest though? XR. Would you do the rest like that? Like X. I mean, I could always do this, you know. XR. Wait, this is the 0 version. Let's do the in general version. In general. R dot S is basically saying this R1, R2, R3. Okay, I think it's fairly obvious that this is gonna happen, but I'll just point it out. S1, S2, S3, and then you'll have R1, S1 plus R2, S2 plus R3, S3. And that's basically the sum of all of those guys, right? You're going to get sum of 3 n equals 1. Rn, Sn. Okay, that does make sense to make it like this. However, let's see. Let's try to do it from the cosine thing, right? The cosine thing. Let's check it out. So, from the cosine thing, you'll get R magnitude, S magnitude, cosine theta. Let's see what this looks like. You're going to get R1 squared plus R2 squared plus R3 squared. Good. And then S1 squared plus S2 squared plus S3 squared. Got that. Good, good. And then after this, it looks like you're going to get, oh yeah, cosine. We know cosine is. Cosine theta. Let's check it out. Cosine theta is adjacent over hypotenuse. Yeah, adjacent over hypotenuse, that guy. And so is it actually adjacent over? Yeah, it is adjacent over hypotenuse. Okay, that's good. Then you could just get cosine theta is adjacent over hypotenuse, which is basically adjacent hypotenuse. Does it make sense to do that though? It's super general. Adjacent hypotenuse. Does it make sense? Like you have something like this, like that. Does it make sense to be adjacent hypotenuse like that? Like this. No, I don't think that's a very good idea to do adjacent or hypotenuse here, because this vector could be larger than this vector, right? So, and then theta is right there. Okay, that seems to mess things up now. How do you express cosine theta? Let me think. It's the y component. What about the y component? What would that make a difference? Hmm. Need to somehow create y component like that. So cosine theta is going to be that guy with that guy. Going to be... Oh man, okay, I remember this in calculus, but... No, I don't remember this. I remember I encountered this in calculus, but I haven't actually done it. But this is the only way for me to solve this way, though. That is already good. That is good. But this one, ooh, it's going to be tricky. Cosine theta, huh? Because this vector could be larger than this one. It would not make a right angle right here. Right angle somehow. So I have to somehow... Okay, let me check my book here. Wait, no. Should I check out a book? Okay, let me think. That's good. And then this guy would make our angle right here, where this is opposite. No, adjacent over hypotenuse. We know what hypotenuse is. It's perfect. But what is adjacent right here? We know this length. This is actually that length right there. What is the x component of this? Okay, I get it now. So the x component of h is basically, maybe not really x component, but the length like right below here. I need to know that. I need to know that one. Make it more general. So this is basically, okay, let's pretend that this is R and this is S. It's S down here. This entire thing's S. S and this is R. It's fine. And S has a magnitude of this. That's okay. And we need to figure out what this tail is for this entire thing to be safe. Unless I would like to know the projection of this guy going right here, right? This one. And we could figure out what A is. So if we could find that projection, we would be able to we would be able to find the rest of this. Ooh. Like for example, this guy right here is a projection. There's a projection of S right here. Projection of S would make it an x component right here, right? So this is probably why they wanted to be along with the x-axis, huh? So that does make sense. Okay, let's do it. I'll do it like this. So projection of that, this is along the x-axis, so xr, that's perfect. And then s prime is that guy, it's going to be here. But it's not exactly going to be xr over here, just so you know. It's the projection of s right here. This is what we want. Not this thing, but this thing right here. I'll call it A. Not the entire vector of r, but right here as well. Maybe this is why they gave us that hint. I'll do that. Okay, so the projection of S over here is basically X, XZ. Yeah, XZ, whatever XZ is. No. Wait, no. It's actually just X. It's X of S. That's way better. Yeah, that's X of S. So this is X of S. Cool. So that means these two cancel out, and it's going to be xr and x of s. So it's basically r1, s1. Wow, okay, that does make sense now. Awesome. r1, s1. Okay. That's fine. let me check if there's any more other things. So this is one instance, by the way, R1S1. Perfect. It's one perfect thing. So one way to do this is to choose your x-axis along the direction of r. Strictly speaking, you should first make sure that the definition 1.7 is independent of the choice of axes. Choice of axes. First things first, you got an independent choice of axes. Okay. So whatever choice that you have, it has to be a projection of S every time. Okay, good. It's independent of whatever choice of axes. So the rest of these guys is going to be 0 plus 0, if that's the case. R2, S2, R3, S3. Got it. Okay, good. Is that enough proof? Because similarly, you could actually do the same thing with the other axes right here. Okay, so we pretty much proved it. So that's the S prime. Yeah, that's projection of A. A is basically whatever projection of R is right here. So, I mean, this is in general. Well, let's see what numbers 1.16 has to offer. Like the thing, the question mentioned. 1.16. Right there, 1.16. Finding scalar product R dot S by equation that guy showed that Pythagorean theorem implies that the magnitude of any vector R is R equals R dot R. Whoa. It's clear that the length of the vector does not depend on the choice of coordinate. Okay, that makes sense. Alright, that's gonna be the more general part, but this is basically the proof of when you have this can be transformed into this. Yeah. The dot product can be transformed into sum of all these R and S. So we loosely proved it? I'm just not very convinced about this one. But I mean, this looks very convincing, right? So R S cosine theta. I'll just say similarly R is parallel to y-axis, R is parallel to z-axis. Do it like this. And it's going to become R0 plus R2 S2. Yeah, I'll do it like this. Equals to R2 S2 plus 0 and equal to 0 plus 0 plus R3 S3. There we go. This is a very similar one to this. Does this deserve to be a QED? I'm not sure, but I'm doing what the question asked me to do, unless I'm missing some stuff. I mean, it's probably the proof here. It's gonna cancel out. We got similarly of this. Fascinating. Okay. I'll take it. What time? How much time do I have left? 24 minutes. Okay. That took a while. Alright, so 1.8. Let's try to do 1.8 now. 1.8. Alright. It's gonna be days like these where I'm gonna take a while to do. Here we go. 1.8. What's up with you? Control V. Nope, doesn't work. There you go. Alright. Use the definition 1.7 to prove that the scalar product is distributive. That is, r dot u plus v is equal to r dot u plus r dot v. Okay, we could do that. Let's see what it says right here. I'll copy you. Let me copy you. Yeah, I wanna copy this. I'll do it like this. Copy you. And Control V. Put you over here. Nice. And where are you? This one, I'll put you over there. Good. And that's pretty much it. Alright. A. Use the definition 1.7 to prove that the scalar product is distributive. That is, scalar product is distributive. Okay, prove R dot U plus V. These are all vectors. Is equal to R dot U plus R dot V. Okay, I'll do it. So R dot product of U plus V is basically this guy. R dot product. Yeah, okay, so we gotta do it like okay, so we gotta do it like this. R1 U plus V dot product of U plus V. Let me wait, no, that's not a dot product. It's gonna be this guy. Wait, U plus V is basically a vector, so I might as well just make it like how would I express this? What if I do this? Because U plus V is a vector. I know that one. This thing is a U vector. It's the addition of each other to be a vector. So it's the U plus V. Okay, I'll do it like this. R1, U1 plus V1, like that. They're multiplied together. Nice. And I'll do it like this. Yeah, this one. And then R2, U2 plus V2. Perfect. Plus R3, U3. Let's see if this happens. Let's see if this works, by the way. U3. Got it. And this equals to R1, U1 plus R1, V1 plus R2, U2 plus R2, V2 plus R3, U3 plus R3, V3. Good. Now let us separate all the U's and the V's from each other. That's good. So R1, U1 plus R2, U2 plus R3, U3 plus R1, V1 plus R2, V2 plus R3, V3. Good. Now would you look at that? These guys are together, and these guys are together. And what do those look like? They are basically dot products. And the dot products, putting it all together, you have R dot product with U. Good. And then this one now, plus vector R dot product with V. And we're done. Look at that. Hence, R dot product of U plus V is equal to this one. QED. Nice. This one's easy. Pretty easy. Very good. All right, next one. Wait, let's pause for a moment. Here you go. All right, next one. B. Let's go. B. If R and S are vectors, whoops. If R and S are vectors that depends on time, prove that the product rule for differentiating products applies to R dot S. That is that. Whoa. Okay. Let me see. If R and S are vectors that depend on time. That is. You know what? Let me just try to check here first. What's going on over here? Yep, everything is all right. Nice. Nice. Okay, cool. All right. What is it saying? If R and S are vectors that depends on time, prove that the product rule for differentiating product applies to R dot S. That is that. Okay. All right. That seems simple enough. Let's try to separate these guys right here. So I'll prove this thing. R dot S is good. Let's separate this into what we saw over here, right? We have, yeah, let's separate this guy. D dt. R dot S is basically saying R1 S1 plus R2 S2 plus R3 S3. Good. Now I pretty much apply the derivative of each of these, right? So d dt of R1 S1. Keep in mind these vectors are dependent on time, okay? D dt of R2 S2 plus d dt of R3 S3. I'm running out of room. Now we could apply the dot product in here. The dot did I say dot product? Now we could apply the product rule. There you go. The product rule over here. So it's basically d dt influence the R1 first. So d dt of R1. Leave out the S1. I'll organize it like this. Leave out the S1. Should I do that? Okay, I'll do it like this. D of dr. There you go. Much better. dr1 dt. Leave out the S1. Plus. Now we influence the S version. The S part, I mean. S1 ds1. R1 ds1 dt. Okay, that's good. Plus this one now. I'll put it like this. Up. Good. And then dr2 over dt s2 plus dr. Wait, hold up. I'll do this again. dr2 ds2 over dt. Yeah, that's fine. So this is the green version. Good. Plus dr3 over dt s3 plus this is a pretty long process, but I'll take it. S3 dr3 over dt. Okay, now that's better. This is I'll make this magenta. Good. All right, that's fine. Now that we have all this, let's gather around Let's check. Let's gather around. What is our goal again? Oh, this one right here. Okay, good. So ds dt and then plus dr dt. So let's gather around all the s's that are being derived, which is these guys. I'll make them blue cyan over here. So let's gather these guy, this guy, and where's the other one? I should have another one. That's not how it goes. Dang it. All right. dr and then let me switch them. It's supposed to be an s and that should be a r. S and this would be r. Got it. There you go. Gather all these together, and you pretty much have a dot product of that. And the other one, gather all these together, and you pretty much have a dot product of that. So the orange one would be, I should put this somewhere else actually. Let me put this over here. B. There we go. B. Okay. And then I gathered them all up. You're going to get this thing. I'll put it right here. S1 dr1 over dt. You know what? I'll gather all the blue ones first. R1 ds1 over dt plus R2 ds2 over dt plus R3 ds3 over dt. Okay, that's the orange version. Wait, no, blue. Sorry. Blue version. Wait, what? No, orange. God damn it. Here's your orange version. There you go. And then plus the blue guys now. Blumen group. R1 ds1 over dt plus R2 ds2 over dt plus R3 ds3 over dt. Yeah, I think we got it. Good. So we got that guy. Now what does this look like? It's basically a dot product of between R and change of S. So let's do that. R dot product, change of S, dt. And then we just have an addition of the, oh wait, did I put R's again? Oh my gosh, I keep doing that. It's going to be, so the, why does this keep happening to me? So R is actually this guy. Let me check again. ds, rds. Okay, so this is actually the blue version. My bad. This is blue. And this is the orange version, which should switch to terms, which I didn't. This keep repeating the same thing again. So this is going to be S right here. It's going to be S here. Okay. S. Make sure it's S. Good. R1. Nice. And then R2. R3. S3. Got it. There you go. So, okay. Let's finish this off. It's basically S1 dot product with the change of R. Sorry, S dot product with change of R. So we, lo and behold, we got it. Done. dt r dot s. Cool. So this is 1.8. Nice. You got it. How much time do you have left? 8 minutes. Oh no. Let me see. Little break here. Hold up. Let me just. That is weird. Okay, there you go. That's nice. Alright, nice. Okay, cool. Now, we got this. We solved 1.8. Nice. Can we move on to another one? I mean, I'm pretty hungry. We have 8 minutes left. Alright, let's see if I can do it. Alright, 1.9. Let's see if we could trudge through 1.9. Here we go. 1.9. Control Shift S. 1.9. It's gonna be this guy. Control V. Dang it, that always happens. 1.9. Let's monitor. There it is. Okay, you're going up there. No. You're going up there. Nice. What does it say? In elementary trigonometry, you probably learned the law of cosines for a triangle of side A, B, and C that guy is that guy. Yeah, I remember that. Where theta is an angle between the sides A and B. Show that the law of cosines is an immediate consequence of the identity a plus b squared equals a squared plus b squared plus 2ab. Okay, so vectors a plus b squared is equal to that thing. Interesting. Okay. Show that the law of cosine is an immediate consequence. Identity, that guy. Nice. How would I do this? Show that the law of cosines is an immediate consequence of the identity. Yeah, they look very similar. I mean, they are some. They should be the same. And let me check. A plus b. It's going to be twice of them. They turn into a scalar? Is that it? Yeah, they do turn into a scalar. Okay, let's try to do it. Show that the law of cosines is immediate consequence of the identity. So I'm turning this thing into that guy right there. Okay, that's fine. Let's do it. So a plus b, they're vectors, by the way, squared is equal to a squared plus b squared plus 2a dot product b. Nice. These are vectors. So let's try to prove it. The right-hand side looks very easy to prove. B squared plus 2a1 b1 plus a2 b2 plus a3 b3. Nice. We'll do that. That's the dot product of that guy. What else? What are we missing? Oh, okay. So a b. Okay, we don't need to do that. We just have to turn it into a and then b cosine theta. There you go. Because that's by definition, right? Of the dot product. Perfect. Now the other one, let me see. The C version. Oh, the C, yeah. So the C is basically, whoops. So the C is basically, for example, this one. This is A. This is B. The C is this thing. There you go. Whatever that length should be. So let's try to figure this one out. A plus B, we add them together. They're vectors, right? That's good. Let's check it out if we could. Can we actually do the A plus B like this? A plus B. They're vectors, so we need to be careful that they are actually vectors. Dot products. Do we need the we need to do dot products for them. Okay, we'll see what happens. So a times a dot product a plus a dot product b. This looks very silly on paper, but I'll see what happens. Plus b dot product a plus b dot product b. Nice. Okay. A dot product a is basically 0. That's fine. This is also 0 as well. 0. And then what else? This should be 0, 0. AB should be some angle. That's okay. AB and BA. Am I doing this right? I don't think I'm doing this right. Minus 2AB. What does it mean to square a... What does it mean to square a vector? Let me try to look this up. What does it mean to square a vector? Yeah. Oh, actually, let me check my book. The book would actually explain it better. Let's see. What am I missing here? Go up a little up, 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 up. Right here, somewhere. Where are you at? 1.17, 1.16, 1.7, 1.9. Ooh. Okay. Where R and S denotes the magnitude here. Let me show you what I'm reading. This guy. R and S. Got this guy. Ooh, I have 30 seconds left. R and S, okay, let's try to do this quick. Data is between them for a proof of these two. For example, construct object to object placement dr. The work done by the force is scalar product f.dr as given 1.6.7. Another important use of the scalar product is to find the magnitude of the vector. Vector or length of any vector r is denoted by r or r. Okay, my Pythagorean theorem is equal to that thing. Okay. Alright, it's fine. I'll do overtime. By 1.7, this is the same as 1.7. It's the same as that guy. Okay. R dot product of the R. Pretty strange. It's often abbreviated as R squared. Ooh. Okay. So this is probably a hint right here. R dot R. R dot R. That should be A. Wait, this should be, yeah, this is R squared. R dot R. Okay. So I was right of doing it like this. Okay, let's do one by one. One by one. Here we go. So A squared. That's good. Plus A B. Nice. Plus BA plus B vector squared. Good. Okay. Let's see what happens with this. Where's my where's the boy at? Oh, here it is. Got it. So this guy I'm gonna get right here. It's often abbreviated as R squared, although this is what people usually say, or we should actually be careful. If C is negative, CR is in the opposite direction of R. Got it. Okay. So That's the differentiating. Scalar product to be SR squared. Okay. C squared. Need to figure this out. I thought A dot product A should be let me think. A dot product A should be A. It's meant to be like that. So, dang. Theta of that, theta is equal to, so 0. Okay, cosine 0 is, alright, I get it now. Cosine 0 is that guy. So A dot product A is what it's saying, right? And this one as well, A dot product B plus B dot product A plus B dot product B. And these guys are basically saying magnitudes. Yeah, so A, basically A. There you go. Plus A dot B. This should be the same. No, wait. They should cancel each other out. Okay, let me take a look at this. How do I prove this? 2AB. How do I prove this thing? Wait a minute, why is there a negative there? Oh yeah, there's always been a negative there. Ah, my god. Man. It's basically B. Let me check again. Squared. Okay, so it should be squared. R dot product R. Yeah, they should be squared. There you go. B, and then these guys should be 0 then, if that's the case. Huh. Okay. Yeah, if I remember, if you flip this, if you flip this, it's gonna be a negative right here. A dot B. I need to know the dot product rules. Let's see, dot product rules. I need to know these. Dot product. Oh, wait a minute. A minus should be a minus. C dot C. What does that mean? What does it mean? Hold on. Hold on a minute. Negative 2A B. Let me try to figure this out. Okay, they should be, yeah, these guys should be the same. It's not gonna make it negative. They're both basically the same, so it's plus 2A dot product B. Okay, I almost had that mistake. That's okay. We got it. And then we have this thing. 2AB doesn't make it like this. Dot product. So C will make it, dang it, show that the law of cosines is an immediate consequence of the identity. Okay. So I made a mistake here. So I'm trying to go from I'm trying to go from there to there then, if that's the case. If I wanted to do that. A plus B is basically saying that guy. Okay, I think I know what's happening. So if I add these two vectors together, right? Like these two vectors together. That's good. So if I add them together, you'll basically get the C part. I think that's what they're trying to say. That is what they're trying to say, huh? Dang. So that's the C, huh? Let me check if I could do this. If I add them together. What you get? Gonna get a C, right? If I add them together, end to end, you'll get this large vector right here. Does it make sense? Does it make sense? Or it has to be subtracted, A minus B. But why is it added? A plus B. Dot product rules. I'm looking at this, by the way. If you want to see. I want to finish this problem before I eat. Okay, here we go. Let's monitor. Nice. Oh, crap. I think I did an oopsie. There you go. And then... okay, let's do this again. So I have this, and then I got this. Let's monitor. Nice. There you go. This is what I'm looking at. I don't know why they had the minus version, but we have the plus version over here. Oh, I think I know that. Actually, no, I don't really see a correlation. I mean, they're practically the same, but I can't seem to understand why they would do. I mean, yeah, it would make sense that you should subtract them like this. So it's going to be end to end. And for example, this guy, Control T, put it over here. It seems to be a logical reason for it to be subtracted. Put you guy over here. Good. So this guy has been subtracted, putting it like the other way around, right? And then they're putting it like this guy. If that's the case. A minus B. This one's a bit stump worthy. Reset it. C squared. So what if I do this? It's just, this thing is basically saying C, right? They're basically saying C. I'm kind of proving on the other side right there. I mean, we know for a fact what this is, right? It's basically A, B cosine. And the one over here is, these guys basically C, and that's a C as well. And you have your C squared, A squared plus B squared plus 2A. Oh, it should be a negative C, huh? It should be a negative C. 2A, BA, and then cosine theta. Ooh. Yeah, well, this one is also like a vector. These are vectors, though. Wait, not vectors. Magnitudes. It's like C squared. Should be a negative then, if that's the case. Wait, no. Should not be negative. Where's this negative come from? We have 2ab cosine theta. All right. I guess that'll be my final attempt for this. But okay, I'll take a look at 1.9 later tonight, and I guess I'll see if I can actually derive this. I'll look at other sources as well, other than this thing. I just extracted that from Google, but I'll try to delve deeper on how to solve this one. Till then, see you guys next time. See ya.